Welcome to part 7 of the video on the hypothalamic-pituitary-adrenal axis. So we've now discussed the HPA axis, and what I want to move on to discussing in this next part is when this axis is actually going to be active. Now it's active on a daily basis, and its activity varies on a circadian basis. So what I firstly want to discuss is that, and then we'll move on to discussing the fact that it can be activated in response to stress. Okay, so let's start off by discussing the fact that the activity of the hypothalamic-pituitary-adrenal axis varies on a circadian basis, and it is often referred to as a classical example of a circadian rhythm. So what is meant by circadian rhythm? Well, the word circadian is derived from two Latin words. The word circa, meaning around, and dies, meaning day. So circadian means around a day. So a circadian rhythm is something that oscillates on a 24-hour basis, basically, with a period of 24 hours. So for instance, the most obvious example is the light-dark cycle. It gets light, it then goes dark, it gets light again, it then goes dark. This is a rhythmic process, and what's the period for the rhythm to actually occur? It's 24 hours. Okay, so in 24 hours you go around a full cycle. So that's an example of a circadian rhythm. Now the hypothalamic-pituitary-adrenal axis, its level of activity also varies on a 24-hour basis. It goes in a cycle, and the cycle repeats itself every 24 hours. So that's why we refer to it as a circadian rhythm. So what I want to firstly tell you about is how the activity actually varies on a 24-hour basis, and then we'll actually go into the mechanism. So how does it vary on a 24-hour basis? Well, the amount of cortisol that you will have circulating in your blood is very, very low during the night. So at midnight and throughout the early hours of the morning, you're going to have very low levels of cortisol within your bloodstream. In fact, let's draw a graph of this. So we'll have time on the x-axis here. So we'll have 0, which is midnight. Then we'll have 4 a.m., 8 a.m., midday, 12, 4 o'clock in the afternoon, 16, 8 o'clock at night, 20, and then you're back to midnight again, which I'll call 0. Okay, so initially it's the level of cortisol, and that's what we'll be plotting on the y-axis here. So this is going to show the level of cortisol. Initially the level of cortisol is going to be very low. It's going to be almost 0, basically. Then as you go on through the morning, so through the early hours of the morning, it will be rising up gradually. So this represents the hypothalamic-pituitary-adrenal axis becoming more and more active. And then towards 8 o'clock it will approach its maximum, and at 8 o'clock pretty much it will arrive at its maximum. So at 8 o'clock it's going to get to its sort of maximum, and then it's going to sort of fall off as the day goes through, but it's still going to be reasonably high throughout your waking hours. So it'll be high here, and then as it goes into the evening, then it will fall back off. Okay, so this isn't an exact graph of what it will look like, but I hope this gets across the main point here, that in the waking hours cortisol is high, and in the sleeping hours at night it's low, and it goes down almost to 0. And of course this represents the activity of the hypothalamic-pituitary-adrenal axis. So we have got cortisol on the y-axis here, but you could quite easily have put activity in the paraventricular nuclei or activity of the corticotrophs, etc., things like that on the y-axis as well. The activity of the hypothalamic-pituitary-adrenal axis, in short. We're just looking at the final product of the hypothalamic-pituitary-adrenal axis, which is a sensible thing to look at, because after all this is the hormone that's actually doing something. Okay. Now, before I talk to you about what is understood, the very basic model for why this occurs, the neuroanatomical model, I just want to explain to you as to why you would want this to be happening. So every day during the waking hours, cortisol is going up, and during the night, cortisol is going down. Let's think about what are the effects of cortisol. Well, we've seen the major two effects are cortisol is going to have effects on metabolism, and it's going to favour the increased levels of all of these nutrients within the blood. So it's going to raise fasting blood glucose level, raise fasting amino acid level, and raise fasting free fatty acid level. Okay, that seems reasonably sensible because during the daytime you're going to be needing more of those nutrients, so it makes sense that you'd want higher levels of those nutrients in the blood during your waking hours as compared to when you're sleeping. So it seems reasonably sensible to have those metabolic effects during the day and not at night. Now, the immune effects, it's more difficult to justify why that would need to be oscillating on a circadian basis, and I'm not going to even attempt it. So I'll just remind you of the fact that we're going to be releasing cortisol on a daily basis, and it's going to have this effect of dampening down the immune system. It's going to be putting a brake on the immune system, both the innate immune system, which is its anti-inflammatory effect, and the adaptive immune system, which is its immunosuppressive effect, and it's going to not completely stop the immune system working. Of course, that's not what we want to do. It's just going to, break it a little bit and stop it from initiating responses that would be very damaging to our tissues. So it stops excessive immune responses, basically. Okay, and it will be doing that on a daily basis. So that's the circadian oscillations then of cortisol. What I want to now talk about is what is it that actually causes this? Why does the hypothalamic-Pituitary-Adrenal axis become active during the day and less active at night? Well, this is all to do with its connections with another hypothalamic nucleus, or other hypothalamic nuclei rather, which are the suprachiasmatic nuclei. So we are going to need to have a little bit of a study of the suprachiasmatic nuclei in order to understand why the paraventricular nuclei are becoming active in this way. So the suprachiasmatic nuclei, and for short the suprachiasmatic nuclei are abbreviated down to the SCN. Okay, so again you have two of these, like the paraventricular nuclei, and I think before going any further in discussing what these really are, I'm just going to show you the anatomy. So let's go back to our picture here of our pictures rather of the hypothalamus. So I'm now going to mark on here where the suprachiasmatic nuclei are present. Now, they're going to be present very anteriorly. They're going to be above the optic chiasm here. And this is the sort of position where you'll have the suprachiasmatic nuclei in orange here, like so. On this picture, they'd be in this sort of position. So again, you have two suprachiasmatic nuclei. You have a left suprachiasmatic nucleus shown in orange here, and I'm just going to outline that in black so that it shows up better. There it is. And there it is. And you have a right suprachiasmatic nucleus. Okay, so I hope again that these two pictures together can give you the understanding of where they are. So again, just like the paraventricular nuclei, they do not take up the full thickness of the hypothalamus. They're just the medial portion that faces into the third ventricle here. Okay, the suprachiasmatic nuclei are more anterior than the paraventricular nucleus. But they're lower down, so there's something above the suprachiasmatic nuclei. Indeed, the medial preoptic nuclei would be sitting above the suprachiasmatic nuclei, but they're not particularly relevant to us here, so I won't add them on. So this is the suprachiasmatic nuclei. So I hope that shows you where they are in the hypothalamus. So they're very close to the paraventricular nuclei, and indeed they're going to have connections to the paraventricular nuclei. So that's where they are. Let's now talk about what they do, because that's the really interesting bit. They are your internal circadian clock. They keep time, basically. They change their level of activity on a circadian basis. So let's draw another one of these graphs. So we can draw another one of these 24-hour graphs, and whenever you're discussing circadian rhythms, you end up drawing loads of these graphs. So 0, 4, 8, 12, 16, 20, 24. Okay, right. So this time on the y-axis, what I want to show you is the suprachiasmatic nuclei activity, i.e. this is made up of loads of neurons. Of course, it's a part of the brain, so it's going to be made up of loads of neurons. How active are they? How many action potentials are they firing? So how often are they firing action potentials, and their rate at which they fire action potentials is determined by whether it is day or night. So during the night, their rate of firing action potentials is very low, and then just like this, towards 8 o'clock in the morning, their rate of firing action potentials goes up and reaches a maximum, and then it will come down again as we go through the day towards the night, like so. So the suprachiasmatic nuclei, they are a bunch of neurons, loads of neurons in the hypothalamus, and their rate of firing oscillates on a circadian basis. They are firing action potentials most rapidly during the waking hours, and they're firing action potentials at a low rate during the sleeping hours, the night. Now, they are going to connect to the paraventricular nuclei, and they are going to cause the paraventricular nuclei to have the same pattern of firing, i.e. that's how the hypothalamic-Pituitary-Adrenal axis is going to end up showing this circadian oscillation as well. So this is the suprachiasmatic nuclei activity, and I'll discuss in a moment how the suprachiasmatic nuclei keep in time with the light-dark cycle. But at the moment, let's just acknowledge that they are this internal clock, and now we want to see how they are going to convey this time to the paraventricular nuclei. So bringing back up the anatomical picture then. So here we have the suprachiasmatic nuclei. Let's have a neuron in here. You're going to have projections from the suprachiasmatic nuclei to the paraventricular nuclei. So this means, and these will be excitatory synapses here, so this means that when the suprachiasmatic nuclei are firing at a higher rate, you're going to end up with the paraventricular nuclei firing at a higher rate, i.e. more activity of the hypothalamic-Pituitary-Adrenal axis. You're going to get more release of corticotropin-releasing hormone, more release of adrenocorticotropic hormone, and more cortisol release. Okay, so I hope you can understand how this means that the suprachiasmatic nuclei are going to transfer their level of activity to the hypothalamic-Pituitary-Adrenal axis. So that's the means by which the hypothalamic-Pituitary-Adrenal axis gets this circadian oscillation because of its connections to the suprachiasmatic nuclei in this way at the level of the paraventricular nuclei. Okay, now just to complete the discussion, let me talk about how the suprachiasmatic nuclei maintain their pattern of activity in time with the light-dark cycle. So they get increased activity when it's light, and they get reduced activity when it's dark. But how do they know when it's light or dark? Because this is a bunch of neurons inside the skull. How do they know when it's light or dark? Well, they have fibers or neurons from the eyes which are telling them whether it's light or dark. So on the retina, there are special cells which are going to be communicating to the suprachiasmatic nuclei whether it is currently light or dark. Now, the retina, for the most part, the photoreceptive cells in the retina are the rod cells and the cone cells. It is not those cells that are going to be communicating with the suprachiasmatic nuclei. It is actually special neurons that are in the retina that are going to be communicating with the suprachiasmatic nuclei. So in order to just motivate this a little bit better, I just want to remind you of the general structure of the retina, and then I think it will fit better in, because if you don't know what, for instance, a ganglion cell is in the retina, then it's quite difficult to explain this. So I'm just going to go over a bit of the retina. So let's say we've got one of the eyes. Let's just draw one of the eyes here. So this is a really simple picture. So this is just showing the retina. I'm not going to draw all the other structures in as well. And let's say we've got the optic nerve coming here. So this is the right eye. We've taken a transverse cross-section, and all I'm showing is the retina here. Let's now zoom in on a piece of the retina. So let's take this little bit here, and we're going to zoom in. So I'll colour this box in. We're going to zoom, zoom, zoom with a very powerful magnifying glass. What will we actually see? Well, remember, it's back to front of what you would expect. The photoreceptors are most peripheral, and then the neurons are more central. So all the light has to come through all of the neurons and then get to the photoreceptors. So drawing this picture, what you'd have is you'd have the retinal pigment epithelium at the bottom here, okay, which is involved in recycling the retinal pigment which responds to light. So here is bunch of retinal pigment epithelial cells. Just give them all nuclei here. So this is the retinal pigment epithelium, not particularly important for what we're discussing, but I'll just put it in there to put everything in context. Then what you'll have is the photoreceptors. So you'll have a rod cell, for instance, here, and here is the actual rod of the rod cell. Then it will be connected to the cell body of the rod cell here, where the nucleus is going to be present, and then you'll have the other process which will pass on the information upwards. So I'll just draw one because they're quite complicated cells to draw. You also have cone cells which will have a slightly different photoreceptor in the shape of a cone rather than a rod. So this is our rod cell, this is our actual photoreceptor. Okay, now when light comes in, it will activate the rod cell, and the rod cell is going to pass on the message to another a nerve now, a neuron. Okay, there's a bipolar cell which has two processes coming off its cell body like so. So this is a bipolar neuron or a bipolar cell. So this is a bipolar because of the fact that it's got two sides. It's got one process and another process. So this is our bipolar cell. And then what will happen is it will pass it on to another cell sitting above that, which will be the ganglion cell. So here will be the ganglion cell body, and then the ganglion cell will send its axon away, and this axon will go into the optic nerve. So the axon of the ganglion cell will come into the optic nerve, and it will go on and on back to the lateral geniculate nuclei, so it takes it quite far into the brain. Okay, so this next neuron here that's on top of the bipolar cells, this is a ganglion cell. To give it its full name, it's a retinal ganglion cell. So this is a retinal ganglion cell. Okay, right, so those are the different layers of the retina, and I'll remind you that this is the visceral side. This is where you then have the vitreous humour up here, and this is the parietal side. So it's back to front of what you would expect. You'd expect the photoreceptors to be on the top. You wouldn't expect the light to have to come right through to get to the photoreceptors at the bottom, but that is the way it's arranged. Okay, so why have I shown you that? Well, this is the way that we usually collect information about light. This is the pathway usually. And importantly, I've shown you the retinal ganglion cells. Now, normally the photoreceptive cells are the rod cells and the cone cells, and they convey the information via bipolar cells to retinal ganglion cells. However, some retinal ganglion cells in the retina of both eyes are very, very special, and these are not connected in these classical pathways to normal photoreceptors, rod cells and cone cells. Instead, they are photoreceptive in their own right. So let me draw one of these now. So here it comes. This is a special ganglion cell now, and you can see it's not part of this normal pathway. This is the normal pathway by which we see. This is how the information that's going to be taken to the occipital lobe of the brain, and which will result in us being able to consciously view the world. This is how all of that information is collected. I'm now talking about a special pathway for collecting information about light, which is going to convey the information to the suprachiasmatic nuclei, and this is not a conscious pathway, this is subconscious information pathways. Okay, so these are special retinal ganglion cells that aren't part of this apparatus here. You can see it hasn't got this process that's connecting to a bipolar cell which is connected to a photoreceptor. Instead, it's just sending an axon over to the optic nerve, like the other retinal ganglion cells, but without any source of the information. So where's the information going to come from? Well, this retinal ganglion cell is actually going to be photoreceptive in its own right. It's going to be a photoreceptor. So this is often abbreviated to a photoreceptive retinal ganglion cell, a photoreceptive RGC. So you have a special population of retinal ganglion cells known as the photoreceptive retinal ganglion cells, and these are the ones which are going to be giving information to the suprachiasmatic nuclei. And let me stress, these are rare retinal ganglion cells. Most of the retinal ganglion cells are not photoreceptive. They just convey information from the photoreceptors, which are the rod cells and the cone cells. So photoreceptive retinal ganglion cells, they have a special molecule known as melanopsin, which is the molecule which is actually going to detect light and cause electrical disturbances in this cell that will then lead to them firing action potentials. So when it is light, the photoreceptive retinal ganglion cells will be being activated more, and they will be firing action potentials at a greater frequency. Okay, so that's where we've overall got to, that in the retina of both of your eyes you have these special, rare retinal ganglion cells, which are photoreceptive in their own right. And these are going to be firing action potentials more frequently when it's lighter, and they're going to be sending this information to the suprachiasmatic nuclei. So let me now draw pictures. So I'm now putting in the optic chiasm here. So this is the optic chiasm with the optic tracts coming out the back. So here's the optic nerve from the right eye, the optic nerve from the left eye, the optic chiasm here, the right optic tract and the left optic tract. Now these axons from the photoreceptive retinal ganglion cells, they'll be coming into both optic nerves, and now we know that the suprachiasmatic nuclei are sitting just above the optic chiasm like this. So what can happen is these fibres can just come out of the optic chiasm and go into the suprachiasmatic nuclei on both sides, and that's indeed what's going to happen. So you'll have them coming up like here, and then they'll just end as far as this picture is concerned because they've gone upwards into the suprachiasmatic nuclei. So this is meant to represent an axon of a photoreceptive retinal ganglion cell. And this pathway for axons from the retina to get up to the hypothalamus is known as the retino-hypothalamic tract. So you've got the retino-hypothalamic tract. Now this is not like a distinguishable anatomical tract. You can't find it like you can identify big nerves. It's a concept. It's the concept that information is going from the retina to the hypothalamus. And indeed, these axons don't all group together to form an actual recognizable structure. Instead, they all just go up at different points. So don't go into an anatomy class and try and find the retino-hypothalamic tract. You won't be able to. It's a concept rather than an actual thing that you can anatomically distinguish. So, retino-hypothalamic tract is just the name for this conduction pathway of information from the retina to the hypothalamus. Okay, and then they just synapse onto cells of the suprachiasmatic nuclei, and that synapse is activatory. And now it all makes sense, doesn't it? Because these are going to be firing action potentials more frequently when it's light. They're then going to be activating the suprachiasmatic nuclei neurons, which will then also be firing more action potentials when it's light. So this then is the way that you keep the circadian clock in tune with the light-dark cycle. So the suprachiasmatic nuclei, they will be firing action potentials now more frequently when it's light and less frequently when it's dark. And now we know that they are going to be connecting directly to the paraventricular nuclei and activating the paraventricular nuclei to release more corticotropin-releasing hormone when it's daytime and less when it's dark. And therefore the hypothalamic-pituitary-adrenal axis comes on during the day and goes off during night. So that's the explanation then of the circadian oscillations of the hypothalamic-pituitary-adrenal axis. Now let's talk about stress. So that's the background activity of this hormonal system. So this hormonal system is working every day in you. Okay, it's coming on during the daytime and going off during nighttime. But you can get a boost to it, i.e. you can get a sudden burst of activity in the hypothalamic-pituitary-adrenal axis in response to some form of stress. Okay, now let me stress that there are different forms of stress. In common popular culture, stress means emotional stress. However, in physiology, there are different forms of stress. It doesn't necessarily mean emotional stress, falling out with your partner, falling out with your parents, any other, your boss shouting at you, things like that. There are other forms of stress in physiology, and I want to mention these. So, the different forms of stress is the first thing to start off with. So, physical stress. Physical stress means like suffering and trauma. So if you get punched in the head, of course that will cause emotional stress as well, but it's also going to lead to a big physical injury, and that counts as physical stress. So some sort of trauma will cause you physical stress. Emotional stress, of course, is a form of stress, so falling out with someone, for instance, will cause emotional stress. Biochemical stress. What is an example of a biochemical stress? Well, a good example of biochemical stress is hypoglycemia. So if your blood glucose concentration goes incredibly low, let's say for instance below 3 millimolar, so less than 3 millimolar, and to convert that into the other one, just multiply by 18, so 33 times 8 is then 24, 54, I think, milligrams per deciliter. So either below, if you go below 3 millimolar, which is I think 54 milligrams per deciliter in the other units, that would constitute a biochemical stress. Okay, and another form of stress is infective stress. So if you've got some very bad infection, this is a form of stress for the body, so infective stress. So those are the 4 major forms of stress as far as physiologists are concerned: physical, emotional, biochemical, and infective. And these can all lead to a burst of activity in the hypothalamic-pituitary-adrenal axis. Now, how this is actually caused is not well understood at all. It's caused by top-down, basically. Higher centres in the brain are leading to the activation of the hypothalamic-pituitary-adrenal axis, presumably by activating the paraventricular nuclei. But I'm afraid I cannot give you a beautiful pathway for this in the way that I could for the circadian rhythms. So overall, when this happens, higher portions of the brain, the more incredible portions of the brain, the less machine-like portions of the brain that we haven't been able to fathom out and work out yet, they are going to result in the activation of the paraventricular nuclei, and therefore the activation of the hypothalamic-pituitary-adrenal axis. And they will result in a sudden spike in your cortisol levels in the bloodstream. Now, why would you want cortisol to go up in response to stress? Well, of course, what are the effects of cortisol? Well, the 2 major effects are that it's going to help raise the availability of nutrients in the bloodstream. It's going to raise blood glucose concentration, raise amino acid concentration, and raise free fatty acid concentration. Hopefully you'll agree that in all of these situations that would be a good thing to do. When you've got physical stress, you're going to need more nutrients to try and heal. Emotional stress, more nutrients will help with that as well. Hypoglycemic stress, certainly raising blood glucose is a good idea there. And infective stress, it's going to help you deal with the infection. Coming back to emotional stress, I didn't really give a good explanation for that. You know, if you're emotionally stressed, then something in your environment is not ideal. So having more nutrients may help to deal with whatever that is in your environment that's causing the emotional stress. Okay, so raising the availability of metabolites is going to be helpful in stress. In addition, we're going to tone down the immune system. Now, you might think that is that going to be helpful in stress, but in fact it is. If you're physically stressed or emotionally stressed, then you don't want the immune system being particularly active in that sort of situation, because you might be in a very dangerous situation. And when you're in a life-threatening situation, potentially, let's say, some bear or something is about to attack you, you don't really want to be wasting time with immune responses. You know, attacking infections isn't your biggest priority if something's about to eat you. And having an active immune system can actually hinder your use of certain tissues. So for instance, if you imagine having inflammation somewhere, it causes a lot of pain, and that prevents you from using that portion of the body in the way that you might like to, in the way that you might need to in order to escape the stressful situation. So toning down the immune system may well help you to escape the current stressful situation. In addition, with regards to infective stress, why would you want to tone down the immune system there? Well, potentially, when you've got an infective stress, a big infection, the desire of the immune system is to launch a massive great immune response, either inflammatory or adaptive immune response. And this could cause a lot of damage to that tissue. So again, raising your cortisol level will help to put a brake on that immune system and prevent it from going over the top and causing excessive damage to tissue. Okay, and with that, I think we will conclude this video on the hypothalamic-pituitary-adrenal axis.